Hi everyone. In this video, we can discuss about the conversion of binary to gray code. Okay, so from this it is clear that we have this binary numbers as inputs. So here we can consider the 4-bit binary patterns. So they are listed here with bits heading as B4, B3, B2 and B1. 4-bit representation means total 2 raised to 4, 16 different patterns are possible, 0 to 15. Okay, so this is actually equivalent to that binary value which is equivalent to decimal 0, and this is for 1, 2, 3, 4, 5, then 11, 12, 13, 14 and 15. And we are expecting the output as the gray code equivalent of each and every binary number. So how to get the gray code equivalent of a given binary number? The procedure is like this. Suppose this is the given binary number. In order to get its gray code equivalent, write this MSB bit as it is here. Then 0 perform XOR operation between these two adjacent bits. If these bits are equal, XOR gives a result that is 0. Next, XOR between these two bits. Again, bits are equal, the result is 0. Again, XOR between these two bits are equal, result is 0. So from this it is clear that gray code equivalent of binary 0000 is 0000 itself. Next is 0001. Binary is 0001. We need to get its gray code equivalent. Write the MSB bit as it is here in this gray code. Then take the XOR between these two bits. Bits are equal. So write 0 as it is here. Then again XOR between these two adjacent bits. 0 and 0. So XOR gives the result 0. Next 0 XOR 1. 0 XOR 1 means 0 and 1 different bits. So XOR gives the result 1. So thus is clear that the gray code equivalent of binary 0001 is 0001 itself. So consider a different case that is 0011. This is the given binary. We need to get its gray code equivalent. Write the MSB bit as it is here in this gray code part. Then XOR between these two bits are equal. So XOR gives 0, 0 and 1. XOR between 0 and 1. Bits are different. So this is 1. Then 1 and 1. Bits are same. So XOR gives 0. So for 0011, the gray code equivalent is 0010. This is the procedure, okay? Next, consider one more case. Suppose 1010 is the given binary. In order to get the gray code equivalent, write the MSB bit as it is here. Here it is 1. Then XOR between these two adjacent bits. 1 and 0 bits are different, so XOR is 1. 0 and 1 next. XOR between different symbol, then result is 1. Again, 1 and 0 bits are different, so result of XOR is 1. Okay, so consider this 1010, the gray code equivalent is 1111. So based on this rule, derive or identify the gray code of each and every binary number and list out here. So this is from our output table, and bit heading is represented here as G4, G3, G2 and G1. The second step is using this output table for each and every G4, G3, G2, G1, we need to derive a simplified expression. For that, we can use that K-map simplification method. So for this G4, where we have this minterms with value 1, for here 8, 9, 10, 11, 12, 13, 14 and 15. And for G3, the ones comes over here like 4, 4, 5, 6, 7, 8, 9, 10 and 11. Okay, and for this G2, this is comes here this 2, 3, 4 and 5. Then for this 10, 11, 12 and 13. And here for G1, the ones comes here for 1, 2, then 5 and 6. Next for 9 and 10. Next for 13 and 14. So these are the main terms corresponding to G4, G3, G2, G1, which is listed here based on our previous output table. Now we can consider the K-map for this G4 first. And while simplifying this, here we have two rows full of ones. Okay, so this is the largest possible group. And for this group, the simplified term is, for these two terms are common. And for these two shared rows, which one is common? First one with value 1. So write B4. Okay, so G4 is B4. And for next G3, two rows are possible. This is the largest possible group, one green group and this blue group. Okay, so for this blue group, which is the simplified expression, these two values are common for all these ones, and B3 with value 0, B2 with value 1. So the simplified form is B3 complement B2. And for this green group, the simplified, these two values are common, and B3 with value 1, B2 with value 0. So the simplified expression for this group is B3 B2 complement. This is B3 complement and B2, or B3 and B2 complement. This is actually XOR operation between B3 and B2. So this is B3 XOR B2. This is the simplified form for G3. Next for G2, is the simplified form. So while simplifying this group, we have B3 common here with value 1 and column wise B2 common with value 0. So B2 complement and B3. Okay, and for this green group, column wise B2 common with value 1 and row wise B3 common with value 0. So B3 complement and B2, which is again the XOR operation between B3 and B2. Okay, so G2 is B3 XOR B2. Next for last one, G1. These are the possible groups, and for that the simplified form is G1 equal to B2 complement and B1, or B2 and B1 complement, which is actually the XOR between B2 and B1. So we have all the expressions for G3, G2, G1, G0 now, and based on the simplified expression, now we can draw this simplified circuit diagram for the conversion binary to gray code. Okay, B3 is directly gives G3 and G2 means B3 XOR B2, G1 means B2 XOR B1 and G0 means B1 XOR B0. So this conversion possible using XOR operation. Okay, so consider the next case, the reverse one, gray to binary code conversion. From this it is clear that inputs are the gray codes and we need to derive the output as binary equivalent of each and every gray code. Okay, so take this 4-bit patterns and consider they are the gray code. We need to get the binary equivalent of each and every gray code. The first one 0 0 0 0, and here the binary equivalent is given as 0 0 0 0. How to perform this conversion? If the gray value is given, how to get the binary equivalent corresponding to it? How to get it? So the procedure is like this. If the given gray is this, then write the MSB bit as it is here in this binary. Next, take the XOR between these two bits, the result bit and the next bit of our input. 0 and 0 bits are the same, so the result is 0. Now this bit with the next bit of input, 0 and 0 XOR, so 0. Again, the result bit with next bit of our input, 0 and 0, the result is 0. So this is the binary equivalent of given gray code. Okay, so this is the procedure for getting the binary equivalent of given gray code. Consider one different example like 0, 1, 1, 1. Suppose this is the given gray code. The procedure is, in order to get the binary, the procedure is write this MSB bit as it is here in the binary part. Then take the XOR between the result bit with the next bit of input. 0 and 1 bits are different. In that case, XOR operation gives the result 1. So now take the XOR between these two. 1 with this 1. 1 XOR 1 means 0. Bits are same. XOR gives the result 0. Now the 0 with next bit of input, bits are different. So 0 XOR 1 gives 1. So this is the binary equivalent 0, 1, 0, 1. Check this answer. 0, 1, 0. So the input is 0, 1, 1, 1. This one. Okay. The corresponding binary is 0, 1, 0, 1. So this is the procedure. So based on this, get the binary equivalent of each and every gray code which is given here. And now the second step is we need to derive expression for B3, B2, B1, B0. Simplified expression for B3, B2, B1 and B0. For that we can follow our K-map simplification method. So the first case. Okay, first case for B0, this is the cam. After putting the zeros and ones properly over here in this cam app, we get this. And here, no combining, no two ones we can group together into form a group. So here, this is the pattern or the largest group possible. All the ones are independently existing here. Okay, no further groups possible. So in this case, the expression is actually G3 XOR G2 XOR G1 XOR G0. We can write the min-term expression corresponding to each and every one and combine using OR operation and apply the Boolean rules, and finally after simplifying this, we finally get an expression like this G3 XOR G2 XOR G1 XOR G0. Okay, so if the pattern is like this, we can directly write this answer as G3 XOR G2 XOR G1 XOR G0. That means the first cell contain a 0, second with 1, next 0. That means zeros and ones, one after another. It gives a pattern like this. Then we can directly write this expression for B0 as G3 XOR G2 XOR G1 XOR G0. But condition is the first cell start with 0, next 1, then 0, next 1. That this particular order. If it is given like this particular pattern, then the answer is, we can directly write this answer as the simplified form as G3 XOR G2 XOR G1 XOR G0. Okay, if the first cell contain 1, next 0, then 1, next 0, if the pattern is like that, then this expression is not G3 XOR G2 XOR G1 XOR G0. If this cell start with 0, next 1, then 0, next board actually, okay, and start with 0, next 1, 0, 1, etc. Then the simplified expression, we can directly write the simplified expression is like this. And for this, next is for B1, and for B1 consider this case. We can try to simplify this. And for this B1, for the first group, the expression is like this: G3 complement, G2 complement, or G1, right? Sorry, for this first case, we can try to simplify this one. If B1 equal to, for the first group, this one. For this one, this is G3 complement, G2 complement, then column wise, which one is common? G1 with value 1. So G1 directly. Okay. Next, for the second group, here it is G3 complement G2, then G1 complement. Next is third group G3, G2, G1. Next is for the last group G3, G2 complement, then G1 complement. Okay. Then try to simplify this using Boolean laws. Take this term and this term, consider these two together, then G1 is common, so take this G1 outside. G3 complement, G2 complement, or G3, G2. And consider the next remaining two terms together. G1 complement is common, take this outside, and remaining terms are G3 complement, G2, or G3, G2 complement. Okay, so this is actually G1 and G3 XNOR G2, or this is G1 complement and this is actually G3 XOR G2. Okay, so consider this expression. This is actually of the form A, B complement or A complement B. Means take A as G1. B means G3 XOR G2. So here it is G3 XNOR G2. XNOR means complement of XOR. So this is of the form A, B complement or A complement B. So the exact expression is G1 XOR G3, G2 XOR G3. Okay, so this is the simplified expression for B1 and for this next one, B2, after simplifying we get an expression that is G3 XOR G2 and similarly for B3, from this it is clear that B3 is actually G3 only. Okay, so from this now we can write the circuit like this. B0 means, sorry, we can start with this G3. G3 is directly given as B3. So B3 equal to G3. Then for B2, B2 means G3 XOR G2. This is actually G3 XOR G2. And B1 is actually G3 XOR G2 XOR G1. So take this as input to this XOR gate and one another input as G1. So this is actually G1 XOR G2 XOR G3. This one XOR G1. Okay. So next one is actually G0 XOR G1 XOR G2 XOR G3. So this is taken as input to this. Another input is G0. Finally we get G0 XOR G1 XOR G2 XOR G3 for this B0. So this is the circuit, simplified circuit for the code conversion from gray code